Static electricity is so easily generated that man has known about it in some form or another since his dawn. All animals have experienced it, even if they have no ability to understand any of it. Humans have been dealing with electricity long before they ever had a name for it. One example man has always had to deal with was lightning. Without knowing the relationship between lightning and the electric eel, there are ancient Egyptian texts dating from 2750 BCE which refer to the fish as the thunderer of the Nile, naming them after the lightning and thunderstorms they experienced. Thales of Miletus is considered to be the first philosopher in Greek tradition. Aristotle wrote in Metaphysics, Thales, the founder of this school of philosophy. Thales was interested in finding the unifying principle of diversity. Thales saw a world of order where everyone else saw a world of chaos, a world where anything could happen if the gods willed it, and there was no way of anticipating the outcomes of the various battles between the gods of good and evil. Thales knew that things could be brought into order, and he sought out the unifying principle that brought together all of the chaos of the universe around him. The arche, the source, the first principle. The universe is alive and full of motion, as opposed to dead and still. This is what makes it so hard to see that there is an arche. Animals and humans and plants grow and move and change and have as a part of them the arche. Animals, humans, and plants need water, or else they die and stop moving. So water is or has the arche. Water seemingly moves on its own. It travels uphill and downhill in rivers. The waves on the shore are chaotic, and it can transform from a solid to a liquid to a gas. Stones and metals don't move on their own, but they can be transformed into other objects, like water can, so they have some of that arche. The principle behind all things is water. For all is water, and all goes back to being water. Thales, circa 570 BC. While Thales was looking for the arche in all things, he discovered and systemized various types of static attraction and magnetic attraction. The fact that these objects caused motion meant to Thales that these objects had some arche. He separated lodestones, naturally magnetized pieces of mineral magnetite, from static materials like amber, which is the fossilized resin from trees. Thales found that when amber was rubbed with fur, the amber would attract straw, whereas the lodestone would attract iron without aid. 2,170 years later, in 1600, Dr. William Gilbert, in his book De Magnet, he wrote all about the types of magnets history knew about. In there, he distinguishes between static and magnets, and coined the term electric, which led to the term electricity. Gilbert hypothesized that this amber effect could be explained by an effluvium, a small stream of particles that flows from the electric object without diminishing its bulk or weight. He also states in that book that the Earth is magnetic, and that's why compasses work the way they do, and he assumed this is why the moon stays with the Earth. In 1663, Otto von Guericke invented the first electrostatic generator, a sulfur globe attached to an iron rod. By rubbing the sphere with a dry hand, von Guericke could generate static on the globe. Von Guericke gave demonstrations of his inventions. However, he would sometimes leave out the scientific explanations in order to leave his audience believing in his wizardry, likely starting a tradition of flashy scientific showmanship. Otto von Guericke and his electrostatic generator, 1672. In 1729, Stephan Gray was experimenting with static using glass tubes, and he noticed that the cork in the tubes became electrostatic as well. And if he placed twine in the cork, that static went all the way to the end of the twine. Gray concluded that the electric effluvium could be conducted through certain materials. Gray transmitted the electrostatic 865 feet with some hemp cord suspended by silk. Gray, in making these experiments, also discovered objects that don't work well, called insulators. and objects that did work well, called conductors. He also discovered induction, where contact is not made and yet an electrostatic effect is still produced. Gray was not just a scientific experimenter though, he was also a showman. Static electric party tricks were now all the rage, and Gray knew how to throw a party. Gray was popular for his flying boy demonstration. A boy was suspended from silk. Static was conducted to the boy near his feet. When this was done, particles of dust, feathers, loose paper bits that were placed under the boy's face and hands would begin to float towards the boy's face and hands. Gray's work inspired two scientists, one being Charles Dufay, who was inspired by the glass tubes. Charles Dufay conducted the amber experiment with a piece of glass, which led to the discovery that there are two different types of static. Dufay noticed that two pieces of amber when rubbed with fur repel each other, and two pieces of glass when rubbed together also repel each other. But when both the amber resin and the glass are rubbed with fur, the two pieces attract each other. For this reason he called the static on the amber resin resinous, and the static on the glass vitreous, which is Latin for glass. Today we call them positive and negative, respectively. The other person inspired by Gray was George Matthias Bose, a scientist showman who saw the flying boy demonstration in 1730. Bose discovered a way to temporarily store static by using an insulated conductor, which he called a prime conductor. One showy demonstration of this idea was called the electric kiss. The prime conductor in this demonstration was a lady standing on an insulating block of resin. A spinning globe, see von Guericke, was used to conduct static to the lady. A gentleman was then to attempt to steal a kiss from the lady, causing a large shock to the gentleman and the lady. Bose also had a trick where he would cause alcohol to ignite into flames, lit by a spark that traveled through the point of a sword. Bose, standing on the block of resin, touches the prime conductor and holds a rapier in the other hand. The point of the sword touches the alcohol in the spoon held by the woman, and the liquid ignites. This led to J.G. von Kleist to attempt to capture Dufay's static fluid using Bose's prime conductor idea. Kleist's idea was simple. Spinning globe to get static. Suspend a large stovepipe on silk such that it can touch the globe somehow. And an insulated glass bottle with alcohol in it, later called a Leyden bottle, corked with a nail in the cork as to touch the liquid in the bottle on one side and also protrude from the other side. He touched the nail to the prime conductor pipe and nothing happened. He noticed, as he was putting the bottle down, that there was plasma in the bottle. Touching the nail, he received a severe shock. The invention went untouched after that, as no one wanted to get shocked like that again. Kleist shared this experiment with a colleague from a different university, Professor Jean Elleman. Elleman worked with Peter Muchenbroek to duplicate the experiment in 1746. I wish to inform you of a new but terrible experiment, which I advise you on no account personally to attempt. I am engaged in a research to determine the strength of electricity. With this object I had suspended by two blue silks a gun barrel which received electricity by communication from a glass globe which was turned rapidly on its axis by one operator, while another pressed his hand against it. From the opposite end of the gun barrel hung a brass wire, the end of which entered a glass jar, which was partly full of water. This glass jar I held in my right hand, while with my left I attempted to draw sparks from the gun barrel. Suddenly I received in my right hand a shock of such violence that my whole body was shaken as by a lightning stroke. The vessel, though of glass, was not broken, nor was the hand displaced by the commotion. But the arm and the body were affected in a manner more terrible than I can express. In a word, I believed that I was done for. And here's Muchenbroek about to get his shock. Benjamin Franklin's experiments with these Leyden bottles led him to grouping them like an artillery battery, coining the term an electrical battery. Likewise, he coined the terms charge and discharge. It was Benjamin Franklin that first called the fluid charges negative and positive electricity, as Franklin believed that there was only one kind of fluid with opposite attributes. Although his theory was incorrect, it did provide the basis of the idea of the conservation of charge, and so his terms are still used today. Conservation of charge states that the net quantity of electric charge, the amount of positive charge minus the amount of negative charge in the universe, is always conserved. Benjamin Franklin briefly experimented in electric medical therapy, using a process called Franklinization, where a patient was charged up with static electricity. He attempted to treat a number of paralytics, first with electric shocks and then with static charging, but without much success. Electrotherapy became a thing both in medical research, which moved away from these failed experiments, as well as becoming a thing in the quackery world, selling this idea off as an alternative medicine. In 1785, Charles Auguste de Coulomb, an engineer and architect, used the results of his experiments with torsional force on metal wires to study electrostatic force. Coulomb in 1784 had discovered that the moment of the torque is, for wires of the same metal, proportional to the torsional angle, the fourth power of the diameter, and the inverse of the length of the wire. Coulomb, knowing the metal, diameter, and length of a wire of silver filament, he was able to reduce the above to the moment of torque is proportional to the torsional angle, or in plain English, the force required to twist the silver is proportional to the angle of twist. Force is proportional to the angle. Since the force is proportional to the angle of twist in the wire, Coulomb needs only to introduce a method of making the twisting wire be a result of equal charges repelling each other. Coulomb invents what is called the torsion balance, and goes into great detail on how to make it, which you can see here, which we will not cover. But if you want to pause and see for yourself, you can do so right now. Okay. Using this balance, Coulomb conducts a few experiments. First, he uses figure 4 to charge both balls in the glass cylinder at the same time, giving them an equal charge. The two balls now having the same charge repel. One is fixed, the other is attached to the silver filament. The repulsion twists the wire, and that twisting is proportional to the force of the two balls' repulsion. The ball is moved 36 degrees. In order to get the distance to 1/2 of the first experiment, Coulomb wants to move the ball 18 degrees on the cylinder ruler. To do this, Coulomb needs to twist the micrometer at the top 126 degrees. 126 plus 18 equals 144 degrees. The micrometer twists the silver filament. To have this distance to 9 degrees, Coulomb needed to move the micrometer 576 degrees. Meaning that Coulomb needed to twist the micrometer 4 times the angle, and therefore 4 times the force, to change the distance between the balls by half. Coulomb's experiment is going to prove this equation. We are going to use the final product here to show just the algebra. Fa is the initial condition. Qa is the charge of one of the balls. Qb is the charge of the other. R is the distance between the two balls, and it will be squared. And K is a constant that basically represents the ability of this force to act through air, or whatever medium it's in. Fb will be our final result. We can simplify this because we know that Qa and Qb are going to be the same, and we can also be specific because we're going to be changing the distances. So we can say that QA and QB are the same thing, so we get Q squared. Whereas we're going to use dA instead of R to specify that this is the distance of the initial, whereas dB will be the distance of the final. We want our final distance to be 1/2 of the initial distance, so we plug that into the equation. If we distribute that squared to the 1/2 into the dA, we get this. Removing the 1/4 from the fraction, we end up getting this. If we pay close attention, we can see that FB equals 4 times KQ squared over dA squared, which is exactly what FA equals. So we could say that FB, our final force, is equal to 4 times the initial force. This means that we need to apply a force which is 4 times larger than the initial force in order to force the distance between the two charged balls to reduce by half. This gives us a fundamental law of electricity. The repulsive force of two small globes electrified with the same kind of electricity is inversely proportional to the square of the distance between the centers of the two globes. Force is proportional to 1/r squared. Secondly, Coulomb charged the balls with the same technique as before, but then touched the fixed ball to a third ball of equal size, see figure 5, therefore cutting the charge of the fixed ball in half. The ball that is able to move still has the full charge. Putting the fixed ball back into the glass cylinder, the balls interact with like charges and repel. However, as the fixed ball is half the strength of the other ball, the repulsion between the two balls was half the distance compared to when both charges were equal. Showing this algebraically again, we have the initial condition and the final condition. In the initial condition, both the balls were the same. What we did in this experiment was reduce the charge of the second one by 1/2 of the first. Plugging this into the equation, we get something like this. Simplifying the equation puts the 2 on the bottom. Removing this 2 from the fraction altogether, we get something like this. We can see then that just like last time, the right-hand side has turned into an FA and some other number. So simplifying this, we get FB equals 1/2 of FA. This means that if we reduce the charge by half, we also reduce its force by half. This is the other part of the fundamental law of electricity. The magnitude of the electric force between Q1 and Q2 is directly proportional to the magnitude of the charges. F is proportional to the magnitude of Q1 and Q2. Altogether then, the fundamental law of electricity is the magnitude of the force is linearly proportional to the net charge on each object and inversely proportional to the square of the distance between them. F is proportional to the magnitude of Q1 times Q2 all over r squared. Meanwhile, Luigi Galvani around 1780 became interested in the work of Benjamin Franklin and electrotherapy. In 1791, he published his discovery of bioelectromagnetics. He discovered that electricity was the medium, the way by which neurons passed a signal to the muscles. Galvani used the Leyden bottle to hold charges for his experiments on frog legs, which led to the discovery of the phenomenon he called animal electricity. This was the first evidence that electricity was related to chemistry, and the term galvanism was named after him by Alessandro Volta. Alessandro Volta was one of the first scientists to repeat and check Galvani's work. Volta was, at first, a supporter of Galvani's animal electricity, but became skeptical of it as Volta suspected that animal electricity was caused by chemicals in animals rather than spontaneously produced by the animal's life force. Volta assumed that the chemicals could be removed and the experiment could be replicated outside the animal body. Volta went on to prove that electricity was generated by chemistry and not solely by living beings in 1799 with his invention of the Voltaic pile. The Voltaic pile was the first electrical battery that could continuously provide an electric current to a circuit. Volta's invention was built on Galvani's 1791 discovery, replacing the frog legs with a brine-soaked cloth or cardboard, making a circuit to produce an electric current. Volta believed that the current was the result of two different materials simply touching each other, and not the result of a chemical reaction. In 1819 and 1820, the concept of electricity and the concept of magnetism was recognized as one and the same by Hans Christian Ørsted and André-Marie Ampère. Ørsted discovered that electric currents create magnetic fields. Ampère was in the audience of Ørsted's science demonstration and was inspired to find out how this was happening. Ampère showed that two parallel wires carrying electric currents attract or repel each other, depending on whether the currents flow in the same or opposite directions. You can see their experiments right here. Ørsted's on the top, Ampère's on the bottom. Although Faraday received little formal education, he was one of the most influential scientists in history. It was by his research on the magnetic field around a conductor carrying a direct current that Faraday established the basis for the concept of the electromagnetic field in physics. Faraday also established that magnetism could affect rays of light, and that there was an underlying relationship between the two phenomena. He similarly discovered the principles of electromagnetic induction and diamagnetism and the laws of electrolysis. His inventions of the electromagnetic rotary device formed the foundation of the electric motor technology, and it was largely due to his efforts that electricity became practical for use in technology. George Ohm mathematically analyzed the electric circuit in 1827. His math showed that there was a relationship between the potential difference applied across a conductor and the resultant electric current, also known as Ohm's law, as we will see later. In 1861 and 1862, electricity and magnetism and light were definitively linked by James Clerk Maxwell. After this was discovered, quickly came the inventions of the light bulb, the radio, telephones, electrical motors, cameras, sound recording, music boxes, etc. Altogether, it took about 2,500 years to go from the discovery of static to the invention of the light bulb. In just 159 years, since 1861, we have gone from inventing light bulbs to using the internet, connecting to billions of humans across the globe through electrical wires, and now inventing quantum computers.